synthesis for coordination of replicas. In a replicated system, replicas copy the state. Every one of them has a private copy of the state, and they coordinate to serve user requests. Replication is widely used. It is used in geo-replicated data stores for low latency. It is used in embedded control systems to tolerate faults. And it is used in handheld devices for offline use. This order of operations across replicas is very important. Strong consistency provides the same total order of operations across all replicas. This simplifies reasoning about these systems, but reaching consensus can be inefficient. On the other hand, weaker notions of consistency are more responsive and more available, but they provide less consistency. For example, eventual consistency in general can reorder operations arbitrarily, and causal consistency only keeps the causal order of operations. It is unintuitive for the end users to specify the right consistency level for each operation. Requesting too much may render the application slower. It may make it less responsive and less available. And requesting too little may compromise correctness. What we notice is that users are not really after consistency. What they really want is integrity. And consistency is just a means to integrity. As an example, consider a bank account with the integrity property that we want the balance to be non-negative. And consider the deposit operation. The deposit operation cannot make the balance negative. So a deposit operation can be executed concurrently with other operations at other replicas without any synchronization and without any dependency. But a withdrawal operation can cause overdrafts. So a withdrawal operation has to synchronize with other withdrawal operations so that there is a total order between the withdrawal operations across replicas. Also, a withdrawal may not be overdrafting only because of the deposit operations in the same replica before that withdrawal operation. So the causal order between the deposit and later withdrawal operations should be preserved. The state of the art for this requires user-specified choices. The user has to specify the consistency choices, or the tool requires annotations. And most of the previous work are crucially dependent on causal consistency. Causal consistency is the weakest notion that is possible in these tools. And even if there's no problem for the application to use weaker notions, they still use causal consistency. We present a tool called Hamsaz that, given a sequential object and its integrity property, it automatically generates a replicated object that guarantees integrity and convergence and minimizes coordination. It uses these weaker notions of consistency whenever possible. We define formal definitions for conflict and dependence, and we define a static analysis that uses SMT solvers to automatically infer these relations. At the core of our approach is a novel new condition called well coordination that at a high level requires synchronization between conflicting operations and causality between dependent operations. And we prove that well coordination is sufficient for integrity and convergence. So given the conflict and dependence relations, we have coordination avoidance processes that reduce coordination minimization to classical graph optimization problems. We also have new protocols, non-blocking and blocking protocols that are parametric, and they provide well coordination. They provide this sufficient condition. And they are parametric, as I mentioned, so they can be instantiated with the results of coordination avoidance, and as the result, we get non-blocking objects. Let us look at an example. We write our specifications as tuples of three elements: state sigma, integrity I, and methods M. We are looking at the courseware use case. The state has three relations: the students, courses, and enrollment, which is a set of pairs of courses and students. And the integrity property is the referential integrity of the enrollment relation. So if the enrollment relation is referring to a student, that student should exist in the student's relation. And we have a similar condition for courses. We have also methods. The register method registers the input student. We specify methods as tuples of 3 elements. The first one is the guard expression that defines the condition under which the method can be called. In this simple example, the guard is always true. The update, which defines the posted state, and the return value. We have methods for add course, enroll, and delete course, and query with the expected definitions. Now I'm going to define the conditions that you're interested in. The first one is convergence. So in this replicated execution, the final state of the first replica is sigma 3, and the second replica is sigma 5, and convergence requires them to be the same. The second condition is consistency that I explained with this example. So we have C2, a method called C2, with guard G and update U, and it is executed in pre-state sigma 2. And the post-state sigma 3, that is really U applied to sigma 2. So we say that this method call is observing consistent state when the guard and the invariant hold in the pre-state. If that is true, we say that this method is experiencing consistent data. A very related concept is permissibility. The only difference is that instead of the pre-state, it requires the invariant to hold in the post-state. So it requires I to hold in U of sigma 2. Okay, so now I want to define a conflict relation. It is defined in terms of 2 other conditions that I'm going to define in turn. State commutativity and a permissible concur. So here's an example of state conflict. We start from the same state in the 2 replicas. The first one executes an add course and updates the state. The second one executes a delete course and updates the state. Then these operations fly to the other replicas and are executed there. And the final states, in the final state, we don't have the course in the first replica, but we do have it in the second replica. So the states diverge. We say that add course and delete course state conflict. But also there are pairs of operations where they don't conflict, and we call them we call that state commutativity. Here's an example. We have add course and register executed in these 2 replicas, and they are propagated to other replicas and executed. And if you look at the final states are the same. So we say that add course and register state commute. Now the second condition, which we call permissible conflict. Here's an example. Enroll is executed in the first replica. It is enrolling an existing student in an existing course, so it is preserving the invariant. It is permissible in this state. The enroll is propagated to the other replica and executed there, but just before that, there is a delete course operation. So it is deleting the course. Now the method call is not permissible anymore. It is violating the integrity property, right? It is enrolling in a non-existent course. We say that enroll permissible conflicts with delete course. And when this happens, we need to synchronize. But there are cases where pairs of methods do not permissible conflict that we call permissible concur. There are 2 cases. The first one we call invariant sufficient. The example is add course is being executed here. It goes to the second replica. And there, it really doesn't matter what the method call before it is. It always preserves the invariant. We call methods like add course invariant sufficient. They never have conflicts with other methods, permissible conflict with other methods. The second case is what we call permissible right commutativity. Here's an example. We have enroll. It is all okay, permissible here. It goes to the other replica. Before that, we have a method called add course. It doesn't cause any problem for enroll. Enroll is still permissible. So we say that enroll permissible right commutes with respect to add course. And we can see commutativity here. Enroll is permissible here. If we move it right, is it still permissible or not? So you saw that I defined state commutativity and permissible concur. The relation concur is defined as the conjunction of these 2 conditions. conditions, and conflict is just the negation of concur. We can automatically infer these relations using SMT solvers, and we usually represent, I don't know why it flies, and we usually represent the conflict relation as an undirected graph. You saw that I could define conflict as permissible right commutativity. Interestingly, dependence can be defined as permissible left commutativity. In that sense, conflict and dependence are duals. But I don't have time to talk about that, and all the details are available in the paper. I invite you to take a look there. We define well-coordination condition as a conjunction of three conditions. Local permissibility, which says that every method call is permissible in its originating replica. Conflict synchronizing, that says that every pair of conflicting methods should have the same order across replicas. And dependency preserving, which says that if a method call is dependent on a preceding method call in its originating replica, then the order of these two method calls should be preserved in all replicas. So these are the three conditions. And we proved that, we formally proved that these conditions are sufficient for integrity and convergence. And our protocols provide well coordination. Okay, now we are given this, we could calculate this graph, this conflict graph, and we are interested to minimize coordination. Strong consistency synchronizes between every pair of operations here. So, so A, D, E, and R and A are the first letters of the methods here. So that's what strong consistency does. But our analysis says that we need to synchronize only between these methods. But we can actually do even more fine-grained synchronization. We can find the maximal clicks and then synchronize in the members of each click. So in this case, A and D can synchronize with each other, and D and A can also synchronize with each other. And D has to synchronize in both click 1 and click 2. So we use an instance of the total order broadcast abstraction for each click. So we use two TOBs here, TOB1 and TOB2. Total order broadcast, or TOB, is an abstraction that delivers all the methods that are broadcast in the same order to all replicas, to all nodes. This is a known abstraction. It uses consensus as the lower level protocol, and computationally it has the same power as consensus. Okay, now let's look at an example of the protocol. We have three replicas here. In this figure, down arrows show requests, up arrows show responses. Arrows above the line show the events for the protocol itself, and arrows below the line show the events for the subprotocols, for the TOB subprotocols. So the first replica is calling an A, the second replica is calling an E, and the third one is calling a D. So according to that allocation up there, again, I don't know why it flies. A is broadcast to TOB1, E is broadcast to TOB2, and D has to be broadcast to both TOBs. So it is first broadcast to TOB1. Now, TOB1 should decide whether it wants to deliver A first or D first. It can deliver A first, although it could choose D. When A is delivered, it is immediately executed. The same happens in TOB2. Eventually, E is delivered and executed. One thing that we notice here is that the order of E and A is different in these two replicas. And it's okay, because they don't conflict. Our analysis and our protocols let them run out of order. For the D operation, finally, TOB1 delivers the method, D, and then it is subsequently broadcast to TOB2. And once it is delivered by TOB2, it is executed. Okay? So every pair of conflicting methods are synchronized this way. Let me add one important point. Methods like D that are members of two TOBs can cause deadlocks if we naively use TOB, because they can wait for each other. We actually use a variant of TOB, but I don't have time to explain how that deadlock happens and how we prevent it. But all the details are available there. And this is only the non-blocking algorithm. I don't have time to talk about the blocking algorithm. There's another graph minimization that we do and another protocol that is non-blocking, that is blocking. Okay, in this limited time that I have, I show you one experiment. Here, we are looking at the response time for each of the methods. Green shows the strong consistency protocol, and red shows Hamsaz with the non-blocking protocol that we saw. So if you look at the response time for strong consistency, it is almost the same, and it's pretty high. The reason for that is that there is synchronization between every pair of operations. But if you look at Hamsaz, then the response time for register and query is almost negligible. It's very small. The reason for that is that our analysis tells us that we don't need to synchronize for those. So they are executed without any synchronization. They skip the expensive paxes. So response time is really low for those. The response time for add course and enroll is also decreased, and the reason for that is that now they are synchronizing with fewer methods. They can be executed more efficiently because they are synchronizing with fewer methods. But if you look at delete course, the response time is actually a little bit increased. The reason for that is that now instead of synchronizing on one TOB, they are synchronizing on two TOBs. So response time is increased. But overall, the response time is significantly decreased. Okay, so to summarize, I introduced Hamsaz, that is a synthesis tool for replicated objects that preserves integrity and convergence and minimizes coordination. We also saw a reduction of coordination minimization to classical graph optimization problems. I introduced well coordination, a sufficient condition for correctness, and I also presented protocols that implement well coordination. I think I have about a minute, so maybe I can actually talk about dependence. So here's an example of dependence. Enroll, and before that we have a register. Everything is fine because enroll is actually registering that student S, enrolling that student S, right? So everything is fine. But in the second replica, enroll is executed before register, and that's not okay. We are enrolling a student that doesn't exist, so this is not permissible. We say that enroll is dependent on register. But there are cases where this is not true. They are independent. That's where we have permissible left commutativity. So we have enroll and another enroll before it. It's absolutely okay if this enroll is executed before that one. It is independent of that. To see the commutativity, here enroll is okay after that enroll in the middle. If we move it left, is it still permissible or not? That's the question. Okay, so it seems like the time is up, so I'm ready for the questions. Thanks so much for listening.
Thank you very much, Mohsen. If anyone has any questions, please raise your hand and come forward. Yes.
So sometimes things just don't commute and you need to use something special like CRDTs, or do they come into picture here?
Very good question. So some of the benchmarks that we support, we work on, are actually CRDTs. So if you specify the counter, for example, this tool will synthesize CRDT counter automatically. Yes, and if you input register, then it figures out that there is a conflict, and it uses synchronization when needed between the writes. Yes?
Mohsen, nice work. I was wondering if the protocols that you synthesize are tolerant to faults.
Yeah, of course. Actually, I didn't have enough time to mention that, but we are using TOB here. And TOB, as I mentioned, uses consensus as the subprotocol. And the guarantee of that protocol is that if at most half of the nodes or replicas crash, then the system can still continue to work. We keep that condition here. So if at most half of the nodes fail, we still can continue working. This is for the non-blocking algorithm. For the blocking algorithm, that's not the case. So we lose something, the nice non-blocking property, but we gain something that's that is this favorable property of having to do less synchronization. So I have a slide here for that. I show you. So you remember I showed this this conflict graph, and I said we have to synchronize there. So the idea with the blocking protocol is that I can find the minimum vertex cover and ask that single node to do the synchronization. So at a very high level, that node becomes the leader in the two-phase commit. So, and then it's good because A and E can execute without synchronization. They become eventually consistent, if you will. But the thing is that if the leader crashes, then that's blocking.
Okay, we have time for one last question.
So similar to last question, so you have this R means register, is that right?
Yes, it's the register for student.
Yeah, when you register students, do you have to also do TOB? I mean, whatever.
No, we don't need to do TOB.
I mean, so does this mean the student registration could be lost if it's not replicated?
So we are assuming eventual consistency. So we are assuming that the message is going to eventually be delivered.
Okay. So there's some implicit broadcasting.
There is a simple broadcast. We can use we use reliable broadcast for that.
Okay.
But reliable broadcast is much less expensive than consensus.
Okay.
Okay. All right. Thank you all for attending this session. Thanks to all the speakers.
Thanks so much.
Lots of coffee.